Hello. I'm doing this on the iPad, so if it looks like I'm looking away, that's because I'm looking at the screen. But then if I look at you, I'm not looking at the screen, so ignore that. Just wanted to go through some of the answers to the Astro quiz you did yesterday, or test as it were, and you did pretty well on the whole. I think the average was about 15 out of 20. Which is not too bad at all. So thanks for all doing that. I know your motivation is probably dwindling a little with having no exams and so on. Gonna try and find some interesting stuff going forward, hopefully to keep you engaged. So what I've done is selected the questions from that test where 7 or more people from the sort of 19 that I've got in the upper sixth got them wrong. So I chose that as the sort of boundary, which meant it was about half the questions to go through, so this is not too long and boring. So I've got this on another screen up here, so if I look up here, I'm looking at the question. You might want to have the question up on a screen or print it out so you can see what it is, but I'll read it out. You can just jot it down as I read it out. So question 1 was actually the first one where 7 people got this wrong. A refracting telescope has a total length of 2 meters and a magnification of 9, and we want to know what the focal length of the eyepiece is. So let me remind you that we've got 2 lenses, really cool drawing, and when the telescope is adjusted as it should be, the focal length of the objective plus the focal length of the eyepiece is that total length. So in this question we're told that the total length is 2 meters, and that's made up of these two, FO plus FE. So expanding on that, FO plus FE we know is equal to 2 meters. We also know that FO over FE, sorry, my cat is currently banging at the doors trying to get in, but she's not coming in. FO over FE it gives us the magnification. Okay, that's a formula that you should know from doing the topic. FO over FE gives you the magnification, which is 9. So I've now got these 2 equations, and what I'm going to do is look at this bottom one here, and there's a couple ways around of doing this, but I'm going to look at the bottom one and get an expression for FE, and I'm going to sub that into the first one. So what that tells me is that FO is equal to 9 lots of FE. So FO equals 9 lots of FE. Just take a look at that and see that you understand that. So FE multiplied by 9 is going to give us FO. So FO is equal to 9 lots of FE. I'll put that into the first equation, and that means that effectively I end up with 9 FE plus FE equals 2. And from there, you're all intelligent. If 9 FE plus FE equals 2, that means that 10 FE is equal to 2, and FE must therefore be 0.2. And that was option C, which was the right answer. So let me just rub that out. Children seem to have stolen all the whiteboards I brought back, so I've been left with like 1. The next question that multiple people got wrong was question 4. So I will scroll down to question 4 if you do the same. Question 4 is to do with the mirrors on reflecting telescopes. It tells us they need different size mirrors to be able to resolve to have the same resolution, if you like, for different wavelengths. Remember when we looked at radio telescopes? Radio telescopes were huge, big concrete things. We looked at the one that was in the James Bond movie. Radio waves have really long wavelengths, so what this suggests is to get a good resolution with a long wavelength, you need a really large objective mirror. So we want these ordered in terms of shortest or smallest mirror, which would mean smallest wavelength, up to largest mirror, largest wavelength. And the waves in that order would be ultraviolet, which is the highest frequency, so therefore the smallest wavelength, then visible, then microwave, then infrared, then microwave. So ultraviolet, visible, infrared, microwave, from shortest to longest wavelength, which is also smallest to biggest mirror, and that was option B. So the key for that one was just realising that the smaller mirror would give the same resolution for a smaller wavelength as a bigger mirror would give for a bigger wavelength. The next one I looked at was question 6. And question 6, and funnily enough, it was a lot of these sort of written ones that you lot didn't do too well on, and you tended to do okay on some of the calculation ones, not all, but some. Question 6 was about the Hertzsprung-Russell diagram, and it said that a newly discovered star has an absolute magnitude of 7 plus 7 and a surface temperature of 20,000. Whereabouts would it be? Now, if I very roughly sketch that diagram, what we've got on the diagram, I'll show you this in a second, is something like this, where we've got minus 10 at the top. Remember, minus numbers are actually the biggest magnitude, the brightest, if you like, down to about 14 at the bottom. It depends which version of the diagram you look at, in all honesty, as to how much of the range of stars they want to fit on. But we're certainly going from minus numbers to positive numbers, and we're going from thousands to tens of thousands in terms of the temperature, and the temperature is getting hotter that way. So with ours having 20,000, we're somewhere near this sort of 30,000 limit, and we're at plus 7, which makes it around about here. I'm doing this backwards on the camera, which for you is bottom left, which is why the answer was B. So let me get rid of that. Okie dokie. The next one I looked at was question 7. And question 7 gives us a list of, or a table should I say, of properties of various stars. Waiting for my computer to catch up so I can actually scroll down here. Okay, and we're told that this group of stars is called the Summer Triangle, Altair, Deneb and Vega, and we're given their surface temperatures, their apparent magnitudes and their absolute magnitudes, and asked which one is furthest from Earth. Now remember, the apparent magnitude is how bright they appear to be on Earth. The absolute magnitude is how bright they would be at 10 parsecs away. So what this means is if the apparent magnitude is brighter than the absolute, then they are closer than 10 parsecs. Brighter means having a smaller number because the scale is backwards, remember. And so we can see that for Altair and Deneb, the apparent magnitudes are both a lower number, which means a brighter value than the absolute magnitudes. So they are both closer than 10 parsecs. Vega is the only one that is significantly further away than 10 parsecs. And so the answer there was C. Moving on to the very next question, question 8. We're talking about a binary star system here. This mouse keeps freezing up. Binary star system. In question 8, Menkalinan, if you say it like that, I have no idea, Menkalinan, an eclipsing binary star, and we're shown that because this is a binary pair, as they go around, the brightness increases to a peak when they're one behind the other and then spreads out again. Their apparent brightness, that is. So we see it takes a dip down to a maximum of about 1.98. Or a minimum, should I say. It's a bigger number, but again, it's a minimum brightness. We're told that the distance from Earth to Menkalinnan is 5.7 times 10 to the 17. What is the value of the absolute magnitude? So we can read off the apparent and we have the absolute. Now remember, the equation, I will write it out here, is as follows. Is this. Our apparent magnitude, which we've got a value of 1.98, we've got a value of our, we've got a value of our, getting myself in a model with my whiteboard, trying not to rub out my working on the back. I've got my two magnitudes the wrong way around there. Make sure your M's are different sizes, otherwise you confuse yourself like I just did. So we want this one, we have this one which we can read off the graph, which was 1.98. 5 log, both in our calculators. D is the distance in parsecs over 10. So the only other thing we have to do here, we have to put in our number from the graph of 1.98, but we also have to put a number in for D. And what we have to put in there is the distance in parsecs. So I want to divide the distance they give me, which is 5.7 times 10 to the 17, by the number of meters in a parsec, which is 3 point something times 10 to the 16. Look on your formula sheet. When you put that number in for D, making sure you use the log button, the log to the base 10 button, we can work all this side out. There's no rearranging required whatsoever, and we actually get a value there of 0.64, which is B. So that was just a case of filling in everything on the right hand side of this equation, making sure that D is in parsecs. That's probably where you went wrong, to be honest. You probably did D, left it in meters. That will have given you one of the other answers from the list. Diet, obviously. The table in question 9, are we doing 9? Let me see, did I do 9? No, we didn't. 9 was fine. We actually all, or very nearly all those by the looks of it, got 9 right. 10, however, we didn't. We were asked in another table which of the 4 stars has the greatest luminosity in question 10. Now, if you look at Stefan's law, which gives you luminosity or power, it's the same thing. It's got a lot of constants in it, but then it's also got the radius and the temperature in it, which are 2 of the things we've got in the table there. And actually, all we need to do for this one, let me just rub out my working for the last one, is for each of those stars, we perform a calculation of radius squared multiplied by temperature to the 4, because everything else in the Stefan's law equation, it's all constants. Okay, it's all constants or numbers that you're given. These are our variables, radius squared and temperature to the 4. So we do that calculation 4 times, and when we do that, we find that Sigma Draconis, option C, has the greatest luminosity. So a surprise to many of you got that one wrong. What question did we do next? That was 10. Next we did 11. So 11 was, I thought, a fairly easy one, but a lot of you got it wrong. So we're given a graph of wavelength, the variation of wavelength with intensity for a particular star called 40 Eridani b. Remember, all stars give out a range of wavelengths of light, okay, but they will always have more of one wavelength than all of the others, and they always take that characteristic shape which it gives you in the question. But there's always a peak, right? There's always one wavelength that there's more of, I'm holding it down there, that there's more of than the others. And if we use that peak, we can actually work out what we call the black body temperature, which is sort of the average temperature of that star. And to do that, we use Wien's law. Okay, so you look at it directly off your data sheet, and That's one thing I haven't left on the screen here. Just give me 2 seconds. So all we're doing is reading off the maximum wavelength from that graph that they give us, and that turns out to be 1.8 times 10 to the minus 9. So we're going to put that in, and you're going to rearrange the equation. So Wien's law tells us that, let's just write this out, that the wavelength, the peak wavelength times the temperature is equal to this number, 2.898 times 10 to the minus 3. So all I'm going to do is divide 2.898 times 10 to the minus 3 by the peak wavelength that you read off the graph, and you will get the temperature. And when you do that, the temperature you get, I've not actually worked it out there. Let's just do that quickly. So we've got 2.898 times 10 to the minus 3, that's the Wien's law number. Divide that by the wavelength we read off, which is 1.8 times 10 to the minus 9, approximately. We get around 160, what's that? We got around about 1,600,000, so 1.6 million. Can't really take my contact lenses out. Got about 1.6 million there, which was option B. Oh, I did read it wrong on the calculator. It was bigger on the screen. It's actually it's actually 16,000. Sorry. However, it's the only one that's got a 16 in it on the answers, so I would still have guessed that right, despite being blind. Question 15 was the next one I did. And question 15 is about cosmic background radiation. Now, a lot of these answers kind of did make sense. They asked us what the assumption was that this background radiation corresponded to a temperature of about 3 Kelvin. Well, it's all based on the fact the universe is expanding, because otherwise the waves wouldn't have stretched in the first place and we wouldn't be receiving them at these really high wavelengths. They initially were really short wavelengths. So although the others do make sense, and I would argue actually, those of you that put C, I don't think you're wrong, because if we're not looking at the Big Bang or the objects in the Big Bang as being black bodies, then this does also fall apart as well. However, I suppose it says space can be regarded as black body, and it can't, because space is nothing, it's the stuff in it. So yeah, B is the sensible answer there. And the last one that a lot of you got wrong was 19. For a black body radiator, the frequency at which maximum radiation of energy occurs is proportional to, and our options are, blimey, they're really small. Small combined with being blind. T to the minus 4, T to the minus 1, T, or T to the power 4. So which one is tells us what the frequency at which the maximum energy occurs is proportional to T. How is frequency and T related? Well, it's actually going back to the same thing here. What Wien's law does tell us here is that the wavelength and the temperature are inversely proportional. Okay, if that goes up, that goes down, because they've got to equal this number. So if the wavelength and the temperature are inversely proportional, then the frequency and the temperature are proportional. Therefore, it's answer C for question 19. Great stuff. Right. That's all the ones that it seemed to me like you had a problem with. Clearly, a couple of people got another one wrong. A couple of people got sort of ones wrong that most people got right. Happy to explain those to you if you send me an email individually, but I don't want to bore all of you for more than 20 minutes. So thanks for watching. You've got a little bit of time left. Hopefully by the time you get my email tomorrow morning with this link, I'll also have thought of something else for you to do. Have a good day. Bye-bye.